Hello everyone, welcome back. This video will focus on the crossed Claisen condensation. This is a reaction that would involve two different ester molecules that react with each other under basic conditions. So I've chosen two generic structures here, and I'm using two esters that both have alpha hydrogens on them. And they are different because they have some carbon-containing groups that are differentiated by R1 and R2. So if we do a Claisen condensation on these esters, what we're going to happen is the base here would be able to deprotonate both the alpha hydrogen of the first ester and the alpha hydrogen of the second ester. Now, there are two alpha hydrogens here. I'm only drawing out one for the purposes of what we are trying to show here. Okay, so both those alpha hydrogens would be deprotonated to the same extent, which means we're going to have two enolates in our system. We're going to have enolate 1, and we're going to have enolate 2. So we'll have two different enolates in our system. And now in principle, enolate 1 can react with both esters because remember that this equilibrium is not favored for enolate formation. We have some enolate, but there's a lot more of the ester present. So when the enolate is formed, it will have an opportunity to attack both of these esters and do a nucleophilic acyl substitution. Similarly, enolate 2 would have an opportunity to attack both of these esters. Okay, so that means from here, I'm not trying to show the electron push mechanism here. I'm trying to show what products are possible here. So from enolate 1, if it attacks the ester, the first ester, what we're going to get is we will get R1, CH2, C double bond O, C double bond O, and Me. And there will be R1 here. That will be the product when enolate 1 attacks. Let's call this ester 1, and this is ester 2. So that's from enolate 1 attacking ester 1. Okay, so this is from enolate 1 and ester 1 attacking, or enolate 1 attacking ester 1. Similarly, enolate 1 can attack ester 2, and that would give us another beta keto ester, which is going to be this molecule. So this is enolate 1 attacking ester 2. And that's not all, because now we have enolate 2, and it can attack ester 1, or it can attack ester 2. So when enolate 2 attacks ester 1, we're going to get a beta keto ester, which is going to be OMe R2. So this is from enolate 2 attacking ester 1. And plus, we will have R2 OMe with an R2 here, and this is enolate 2 attacking ester 2. Now I'm just showing the product possibilities here, but essentially what we're saying is that when this reaction happens, we can get a total of 4 products. So very similar to what we saw in case of a crossed aldol reaction. So if you haven't watched that video, I would encourage you to go please watch the video on crossed aldol reaction. But the point is, when you have two different esters, again, you have possibility for making 4 different products here. And so how do we avoid this? We apply some strategies. First strategy is to use only one ester with alpha hydrogen. So of the 2 esters that you're using, only one of them should have alpha hydrogens present in it. So that means we could have a combination like R1 ester plus R2 ester. So we're basically implying that there are no alpha hydrogens in this second ester that it can use or that can give you an enolate. So you'll use an ester with where you will use a combination where only one of the esters has alpha hydrogens present in it. And the second strategy is to use a strong base such as LDA so that you can get the enolate quantitatively. You can complete the enolate formation quantitatively. So what the reaction would look like is, if I take this one first ester, which has alpha hydrogens in it, and if I add LDA to it, that's going to give us the enolate from that particular ester. Okay, so that's the first step. In the second step, we are going to bring in the second ester, okay, that one. We're going to bring in the second ester, so R2, C double bond O, Me. And so essentially the enolate is going to attack that acyl carbon, and it will give us a tetrahedral intermediate OMe. And then we have this other carbon that's connected to it. So we'll have the beta carbon with R1 group on it, and it will have the C double bond O and OMe on it. That would be our intermediate. When this alpha carbon attacks the acyl carbon here. And now when this tetrahedral intermediate collapses, the methoxide will get kicked out. And so that's going to bring us to R2, C double bond O, C double bond O, Me with R1 here. So we've made the beta keto ester product that way. So we can basically control the reaction a little bit more. Now, if there is excess LDA present here, then the second alpha hydrogen here would get deprotonated. Okay, if there is excess LDA, that would get deprotonated. So with excess LDA, that's going to give us the enolate from there. This is R2, this is R1, and we have the negative charge. And that would be the step that would push this whole equilibrium in the forward direction, because here you could have some equilibrium in that particular step here. So that would basically push this equilibrium forward. Even the methoxy here that's getting kicked out, that can deprotonate. Okay, so or the methoxide that is getting eliminated here, that can deprotonate that, and it would give you the enolate. And then we finally do the acidic workup, and that would give us the product, which is going to be this beta keto ester. That's the beta keto ester product that we make under these conditions. Because remember that we make the beta keto ester and it gets deprotonated at the alpha carbon to pull the equilibrium in favor of the product. And then when we reprotonate, that will give us the beta keto ester back. So that's our beta keto ester product. So that's our beta keto ester. Okay, so that's the crossed aldol reaction, where for a successful reaction, what you want to do is you want to apply two strategies. You want to use only one ester with alpha hydrogens in it. And second, you want to use a strong base so that you can make the enolate quantitatively. You don't want an equilibrium here, because if you don't use a strong base, then the enolate that's formed, it can react with the starting ester, and that would still give you two products in your reaction mixture. I hope you find the discussion helpful. Bye.